Hey there, guys. So today I want to talk about the statistical universe again. I've talked about it before, but this is going to be one of those slightly more philosophical lectures, mini lectures or lessons. But it's an important concept now while we're developing our statistical toolbox, because I always want you to be thinking about the statistical universe that you are trying to make inferences about. And in fact, if we were to define statistical universe, we can simply say it is that realm about which you wish to make inferences. In other words, it's the group that you're asking questions about. So, for example, if you are comparing a sample mean to a hypothesized mean, and we're going to talk about this test in class, so we're going to compare a sample mean, and how do we symbolize a sample mean? Y bar, right? So compare a sample mean to a hypothesized mean. This is going to be one of the first simple tests that we learn how to do using SAS-jump. What does the hypothesized mean? It's going to be mu, okay? So remember what mu is referring to. This mu is the true population behind our sample. So that true population is our statistical universe about which we're wanting to make inferences. And so what we're really asking when we're comparing a sample mean to a hypothesized mean is, what is the chance given that sample size, what is the chance that Y bar, which is the mean of the sample, would be obtained with a sample size n, okay, when the true mean is mu. And this is a nice way to think about this question. So we want to ask, could this sample mean Y bar have been obtained from a population whose true mean was mu? So really what we're saying is, what is the chance that we would get that particular Y bar? And we need a test for that. And that's what we're going to develop in class. Okay, so that's one kind of question we'll be addressing about statistical universes. And we'll be sampling, in this case, from one statistical universe. But sometimes we want to sample from two universes. And we could call them A and B. And we're really asking, are these universes identical? Okay, are they equal? Are they the same universe, in fact? And very often in statistics, we're going to be having the null hypothesis be that mu for universe 1 and mu for universe 2, A versus B, are in fact the same. Okay, so let's give an example of that. So let's imagine we have our y variable is height, and we're measuring heights of males versus females. So A, our statistical universe A is males, and our statistical universe B is females. And we're asking if heights are different. Now, obviously, if we're going to try to make inferences about all males, that's going to be a really tough sampling problem. And to be statistically honest and rigorous, we want to say how we sampled, okay? Because all males on the surface of the Earth are going to be difficult to sample. So we're going to need to usually have some kind of a subset of males. For example, it might be that we're dealing with college-age males. And, you know, if we sampled just at West Virginia University, we would have to, if we were trying to make inferences about all college-age males, we would have to assume that West Virginia college-age males are no different than all the others. So that might not be a good assumption. So we might have to add to that from WVU. So you can see we're narrowing our statistical universe here. We're making it more specific and less general. And if we were measuring just in a biometry class, we would have to say who took biometry. Now, if we measured every male in the biometry class, we would be measuring the entire population. We wouldn't really have a sample, we'd have the whole population. So maybe we are willing to make the assumption that biometry students are no different from any other classes at WVU, and we are able to generalize about college-age males from WVU. But we wouldn't want to probably assume that WVU males have exactly the same height as males from, I don't know, University of Alaska Fairbanks, for example. All right, and the same thing for females. Do we want to measure all females? Virtually impossible. So we might have to narrow our group down. And when we report our results, we would have to be very careful to specify our statistical universe. So that's one of the points I wanted to make today, is for intellectual honesty and rigor, you have to specify your statistical universe. You must state your statistical universe. What is the population that you are sampling from? And what are you assuming about that population in terms of its generality? Okay? Very, very important, because many specific studies have been done that show later on, when you broaden the population, not to be generally true. Okay, so what are we asking when we ask whether males and females have the same height? Okay, so we're asking in that case, our null hypothesis is mu for males equals mu for females. It's kind of a question, and we're going to come up with some probability. So when we get a sample that has y bar for males and y bar for females, we're going to test whether that hypothesis is true. So in a way, this is our null hypothesis, that they are in fact equal, and yet when we get a particular value, for example, I don't know, let's measure in centimeters, right? So 162 centimeters is our mean here, and the mean we get for females is 151 centimeters. So we're asking, what is the probability we will get these two values given an n of, let's say, I don't know what we have in this class, maybe 12 and maybe 16. All right. So these are the sample sizes that gave rise to these particular values. What is the chance with these sample sizes and these values that I could get these two means drawn from a population, a single universe, or do I have some effect of actually being male versus being female in terms of height? In other words, is there a difference between these populations? Or another way of thinking about it, so the alternative hypothesis, the null is that we have one statistical universe. The alternative hypothesis is we have two universes here, two height populations. Male does not equal female. I'm using symbols and letters. But anyway, the point is, our statistical universe, our question in this case is about the statistical universe. We define it in terms of college age females and males from WVU. We're assuming that the biometry class represents those, and we get some value out for males and females, and we will develop a test that will test this null hypothesis. They were actually drawn from the same population. And what we're going to really develop with that is a probability that that is true. We won't know for sure because we haven't measured everything. We haven't measured every male and female at WVU. If we did, we wouldn't have to even do a test. But since we're drawing a sample, we're finding, look, the numbers are not identical. We can't yet tell, though, whether this is a significant difference. We need to attach a probability to the notion that these are actually drawn from the same statistical universe. And that probability is a key concept that we're going to develop in the next, I think it's the next lesson. Yeah, it is. All right, so you'll watch that then. All right, so a little more about statistical universe. I want you to keep thinking about that. Keep remembering that every sample is being drawn from a much larger population about which you're trying to make inferences. And sometimes we're asking about one universe and how it compares to maybe a parametric mean or other property of that universe. And then in some cases we're asking, are we really drawing samples from two universes, or are we correct in assuming they're being drawn from the same universe? So those are a couple of simple tests we're going to develop early on. Then we're going to generalize that, and that's going to become something called analysis of variance. Okay.